Okay, so let's get started. Today we will continue the discussion on replication and consistency that we started last time. Okay, last time we had all these different consistency models, consistency guarantees, and so on. And we ended with epidemic protocols and eventual consistency. We are done with that part. We will come back to replication. Okay, and today we'll talk about how can we actually implement replication. Okay, and we'll talk about remote write and local write protocols. We'll talk about quorum-based protocol. There is a part 3 because I think I did add some slides to the lecture which are going to be on fault tolerance. So we'll start talking about fault tolerance and failure recovery, which is related to replication. Okay, so let's start with replication. So we already mentioned when we talked about consistency that usually in distributed systems, you have to replicate data or code. And when you replicate data, you have to ensure that they are consistent. But then the question, the other related question is, how is replication actually handled? How do you ensure when a read request comes in, which replica handles it, and so on? So we'll talk about, forget about consistency for today's class. We know how to do it. And we'll start talking about replication itself. And we'll start with primary base, is fairly straightforward approach, and then we'll end with replicated write protocols where you do not have a primary. Okay, so in the primary base there is a coordinator that's coordinating every data item. All the replication is handled by the coordinator. In the replicated write, there is no coordinator. It's a decentralized approach for replication. So those are the two techniques that we will talk about today. Okay, so let's start with a simple technique here, which is a primary based protocol. Okay, so here is a picture that you can see. There are several disks that are shown here, but for the perspective of our discussion, the one that says single server for item X is the one that is actually the coordinator for data item X. Okay, so we are only talking about single data item at this point. The data item may be replicated at multiple of those disks that are shown here, but there is one coordinator that's actually handling them. Okay, so the question is, how are reads and writes handled? Okay, so without replication, it should be clear how you will handle this. When the client sends reads or write requests, there is no replication in the system initially. There's only one copy that's going to be at that server. That's the primary. So all the reads and writes are forwarded. So you'll see that a write comes in, then it's sent to the coordinator. Coordinator performs the write, sends back the result. Read comes in, sends it to the coordinator. Coordinator performs it, sends this back. Okay, so this is the simple no replication case. Okay, but now let's assume that you have replication, which means that there is a primary or a coordinator, and there is a backup server which is storing an extra copy of the data item. Okay, so now what is going to happen is every time there is a write, it's going to come to the coordinator. The coordinator has to forward the write to all the replicas so that all the replicas are consistent with one another, right? So that's what you will see here. Lots of arrows, but what you will see is that when the client sends the write, okay, so that write W2, it goes to the primary. The primary is going to broadcast the write to all the copies. So you will see W3, there are 3 arrows, right? So it went out to 3 of the other disks, excuse me. And then you get back acknowledgements. Once you hear back from all the replicas, you're going to return a result back to the prime. Okay, so this is called primary based, right? So you will essentially have a coordinator, right? So I'm going to show you, this is your coordinator. So let's say the coordinator write comes to the coordinator. The coordinator is going to send it to all the 3 replicas, which are shown here, R1, R2, R3. And then you will wait for all the responses to come back, right? And then you send back the response to the client. So essentially, you get the write at the coordinator, it does the replication, and then it sends back a response. Okay, this is called a very simple remote write protocol. Okay, now question is, what do you do when there is a sorry, excuse me, we should also talk about reads in this case. So when the client is then going to make a read, it can go to any of the replicas because they have been kept consistent with one another. So this client will simply send a read to its local replica. get back a response. So there's no other need to go to the coordinator. So reads are going to be local. The writes are essentially sent to all the replicas. Okay, simple technique. Okay, here is a technique where the primary or the coordinator for the data item keeps changing based on where the reads and writes are happening, right? Excuse me. So we still have that server that's shown as the master for item X. Okay, now suppose this client that is shown in this picture starts accessing data item X. Okay, so in the previous case, you have to send the writes to the primary. Okay, but another optimization that you could perform is, because this client is actually sending all of its requests to its local machine, the local disk that's shown there, that's a server, you can move the primary from the current primary to the local one. So the primary or the coordinator changes. So this becomes the coordinator. Okay, and then that can start handling all of that request. Okay, now if you are only performing reads, that's easy. You're just going to go to the local data item. But even if you're performing writes, you can just send it to your local replica, which is then going to broadcast it to all the others. Sorry, local coordinator is going to broadcast it to other and get back acknowledged. Right? So in this case, the coordinator for the data item will shift back and forth depending on which clients are accessing that data item. Okay? When we talk about the network file, the distributed file system, the network file system, we are going to come back to this concept. We'll see that the quote-unquote server for a file can actually shift depending on where the reads and writes are happening. Typically, the server doesn't change. It's one machine, but you can actually move the primary from one server to the other depending on what optimization you want to perform. Okay, but still fairly straightforward. This is local write. So here is essentially what is going on with all of these arrows. So you will see now the client send the writes to its local machine. Okay, that's W1. You will see that the old primary has now moved to that other machine that now become the new primary, and then all further writes are going to be broadcast. So you will see that W4 is a subsequent write that's actually broadcast to all of the machines. So you moved the primary, but you're still doing the task of the old primary by broadcasting all the writes to other machines. Okay. Yes, your question. Yes. So the question, yes, that's a good question. The question is, how do you decide when to move the primary to that server? So as you can see, W1 actually arrived to the local machine. Local machine will actually send a message here, and that will just transfer that's why the W2 is actually coming back. That will transfer the responsibility to the to the new machine. New machine will perform the write, and then you will either reply to the client or send back acknowledgement. Right. So yes, you have to communicate with the current primary. In NFS, as we will see in a couple lectures, you will ask the server saying, can I become the new primary? The server may say yes or no. If it's no, then you are back to the remote protocol where all the writes go to one server. If it says yes, then the server becomes the new primary. Okay, question is this going to happen for single writes or multiple writes? So if there's only one client accessing a data item, you can move the primary to the local machine, that where the writes are happening. Okay? And that is going to be more efficient because the writes are hitting the local machine, and that's faster. But if there are two clients, let's say there are two clients in this example, if both of these clients are performing writes, you cannot have two primaries. You still need one primary. So either you keep the remote machine the primary, you don't move it at all, or one of these clients takes over the responsibility of the primary and the other one is still getting remote access. Right? So when there are concurrent writes from multiple clients, then you may not choose to move the primary at all. It's better to keep the server that was already the primary as the current primary. So this optimization will only work if there is one client writing. Others may read. Reads are fine. But there should be only one writer. If there are multiple writers, you're not going to move things back and forth. Okay? All right. So that's local writes. But now let's talk a little bit about replicated write protocols because we want to now say this notion of a primary is not something we want. Maybe the primary fails or something like that, and that's not resilient. So what can we do? in this case by having no primary at all. Okay, so you have a set of replicas. The replicas can make updates. Okay, and you still want to ensure consistency. Okay, so there are two ways we are going to do replicated write protocols. One is called synchronous, the other is called asynchronous. Okay, so it's important to understand the difference between synchronous writes and asynchronous writes when you have replication. Okay, so first thing is we should know what synchronous and asynchronous mean. Okay, synchronous, as I have said multiple times, you can, whenever I say synchronous, you should think blocking. Okay, whenever I say asynchronous, you should think non-blocking. Okay, so when you do synchronous writes, okay, that essentially means it's a blocking write, which means all the replicas have to have seen the write and responded before the write returns back to the client. That is called synchronous write. Okay, so if you have a client, C, okay, and then there is this is your primary. Okay, so in synchronous write, the write comes here. The primary has to send it to all the replicas, say R1, R2, R3, okay, and then have responses come back, which say that acknowledgements come back, and the client is going to be blocked until that. Client will not get a return from the write, and once the acknowledge comes back, you will essentially, the write will return saying it has completed. Okay, so in some sense, replicated writes, not replicated, synchronous writes guarantee that all the replicas have been updated, okay, before the client is told the write has completed. Okay, so that is good for consistency, because you will, when the client says the write is done, you are guaranteed that every replica has been updated and has the most recent update of the data item. Okay, but it's also, from a performance standpoint, is quite slow, because the client is blocked until all of these writes are broadcast, and moreover, the write proceeds at the speed of the slowest replica. Okay, if one of these R1, R2, R3 were a distant machine, okay, the time to send the write over a network will be much longer than the other replica. Okay, so you are going to be, the write's throughput is going to be based on the slowest replica in the system. Okay, that's basically a fact of how this synchronous writes work. They're good for consistency, but they're not great from a performance standpoint, especially if some replicas are further away from other replicas. Okay, now, yes?
In this replicated write protocol, is the read function from a different client also blocked?
Question is, in a replicated write protocol, is the read from a different client blocked? That's your question, right? So unless there are additional locks at the application level, from a file system level, reads and writes are concurrent. So if there is a write in progress, some other client comes and reads it, you will read the file. Okay, the file system is not enforcing any higher level application semantics. Now, if that is a shared file, from an application standpoint, maybe you should have put a lock when you did this. But from our perspective, we are just performing reads and write. We don't worry about does the application have a lock or not. So that's up to the application semantics of what it is trying to achieve. So assume that if there's a read, it will come and basically read the data item while the write is in progress, right? Because that's a file system. All right. Asynchronous write. Okay, so in asynchronous writes, as I said, it's non-blocking, right? So the client will send a write request to the primary. Okay, the primary can immediately say, I received the write, and the client can proceed, and all of what I've shown here can happen in the background, and the client can have progressed and moved ahead of this write. Okay, so it's non-blocking. So from a performance standpoint, it's very good, because the client is not blocked. If there are remote replicas, all these messages don't have to be dealt with before the client can continue. Okay, so from a performance standpoint, it's very good. From a consistency standpoint, it's not great. Okay, because what can happen is the client will say, okay, update this file. Okay, you immediately get back a reply, because you are just sending a write request. It's like sending a print or a read request. So you send a read request returned. You as a developer assume that when the read returns, then the file has been updated. That's what your assumption is, right? But clearly, it has not been updated in a replicated scenario, because all of these additional messages are going to go later. Client has already assumed that the write is completed, but in the system, it's still in progress. Okay? Now, if there is a crash, let's say the primary crashes before it could send all of the replicas these messages, and then you reboot the machines, you will see that the write is actually not finished. But the client assumes it has finished because the client got a reply saying the write was successful. Right? So consistency is not going to be guaranteed in an asynchronous write protocol, but performance will be better. Okay? Is that clear? Right, so which one you pick actually depends on the scenario. If you have critical systems where you cannot actually compromise consistency, let's say it's bank database or financial databases, you will do synchronous writes. Okay, because you want to make sure that there is no problem from a consistency standpoint. So you will pay that extra price, performance might suffer. Okay, but if you want high performance, you are not as worried about consistency, you can switch to asynchronous, right? Okay? But by and large, anything that you see that is more critical, like bank databases or anything like that, they stick to synchronous, right? Okay, and because they don't want to take a performance hit, these replicas cannot be really far away from one another, otherwise the performance will really suffer, right? So you will see like banks will put a second replica maybe 5 miles or 10 miles away, okay? Because that's the latency you can. If you put them 100 miles away, that latency starts showing up, and all the performance of your applications that are working on this file system or database will start suffering. Okay? So not so in asynchronous writes, you can have the replicas as far away as you want, okay? But consistency is not going to be an issue. Those questions on that, yes. Okay, question is what happens if a replica blocks in the synchronous write? That's your question, right? Yeah, so if the replica blocks in a synchronous write, the primary check, because it is waiting for responses from the replicas, it could simply send a message to the client saying the write failed. Because remember, you are just reading and writing, you can always get an error message saying the write didn't succeed for some reason, which happens even in normal file system, right? Maybe the disk is full, so if you try to write to a full disk, you will get an error, right? And then the application has to deal with it. So you could certainly send back a response saying the write failed, and then the replicas can be told not to can undo the write or something like that. So you can add some logic to deal with failed writes in the system. Okay. All right. So this is replicated write. So I have the more complicated sequence diagram that shows that simple picture I showed you already. This is synchronous. You will see that the client sent a message, write message to the leader, the coordinator. The coordinator is sending that write to all the 3 replicas, which are called follower. All of them have to send an acknowledgement saying the write was successful. Okay. Once that acknowledgement comes, you will send back a response to the client. Okay. So from the sending of the request to this, the client is blocked. Okay. So it took all of that time for the write to complete. So it's from a client's perspective, a slow write. Okay. But it is consistent. And here is essentially what happens in case of asynchronous. So you will see that the client sent a request to the leader has sent this write request to 3 followers. So at any point, once those requests have been sent, the leader can respond to the client saying write has finished. Okay? In this case, we are waiting for at least 2 of the copies to have said okay before you are sending back a response, not the third one. Okay? But you don't need to even wait that long. You could have sent it right after the write was received or right after the write was sent to all of the clients. Depending on what type of asynchronous replication is being implemented, you will get an acknowledgement well before the entire operation has finished. Okay? This will, from a client's perspective, it is faster, okay? But it's not going to give you consistency if there are crashes. If there are no crashes, everything is good. You will still complete the write in the background. Is that clear? Yes, question. Okay, question is what happens if the replication fails for one of the replica? That is going to depend on the storage system or the file system. Clearly, for consistency reason, if the replication fails for, let's say, replica 3, you have to retry and make sure that eventually it gets all the writes that have not reached it, right? But that's an additional failure recovery logic that you have to implement. This technique is simply saying from a client's perspective, when do you get an okay saying your write finished, right? So all it's saying is you don't wait for all the replicas to have finished the write. But then orthogonal question is, and the same is true for synchronous, what happens when there are failures? How do you deal with them? So when the failed machine comes back, it has to be resynchronized with the rest so that the states are again synchronized. Otherwise, you will have some writes that have never reached that replica. Okay. All right. So that's synchronous replication. But now we will actually talk about a different set of protocols, which is no primary. Okay. So we'll have no coordinator. This is leaderless replication. So any replica can be allowed to update. Okay. And consistency here will be a little more complicated. Excuse me. So this is called, this class of techniques are called quorum-based protocol, because we will see that you need a quorum of replicas to agree. Not every replica, but you need a quorum. Okay? Because you are not going to wait for every replica to answer. You can pick some subset of the replicas. You can perform the write on that subset. And so long as that subset agrees, we will say that the write has been successful. Okay? And because now the writes are going to a subset of the replicas, the reads still have to be consistent. Okay? You do not want your read to actually read from a machine that was not part of the most recent write subset and return some old data. Okay? So how do you design a technique where the writes are not going to all of the machines? Okay? Until now, we said writes are going to all of the machines. But now we will relax that assumption. There is no leader. We will send the write to only a subset. Okay? And we'll still guarantee that the read can never return outdated results. Okay? How are we going to do this? We are going to essentially use quorum, and we are going to use voting. Okay? So you will ask some subsets, we'll send the writes to some subset, we'll send the reads to some subset, and we'll always assume that you vote on the results, and if the results match, then we will say that that's the right result to return to the client. So we need to now design a technique where you no longer send the writes to all of the machines in the system. You'll send them to a subset, any arbitrary subset based on some rules that we will decide, but any arbitrary subset that the client chooses, and yet we will ensure that you will never get old results. Okay? So this will be called quorum-based techniques. There are a whole class of protocols, but we'll see a simple one that's called Gifford's quorum-based protocol, and we will essentially use the following rules. Okay? We have to essentially pick two quorums. Quorums basically mean these are the number of machines you need to perform an operation. Okay? So we'll have a write quorum. Okay? So write quorum is a number that says the write operation has to be performed on those many machines from the overall set. Okay? And we'll have a read quorum, which says any read request has to be sent to all of those machines, and the results that come from those machines have to match for the read to be successful. That's called the read quorum. Okay? So you have to pick, assuming there are n servers, you have to pick a number that represents the write quorum. You have to pick a number that represents the read quorum. And here are the rules of how we are going to do this. Okay, the sum of the read and the write quorum has to be greater than n. So if n is, let's say, 10, okay, you can say write quorum is 7. That means you perform the writes on 7 out of 10 machines. And then the read quorum has to be at least 4. Okay, so that 4 plus 7 has to be greater than 10. Okay. The write quorum has to be always strict majority. Okay. You cannot pick a write quorum that's smaller than half the machines in the system. That's our rule. Okay. So these are our two rules, and implicit in these two rules is also that the write quorum is always bigger than the read quorum. Yeah, because we say nr plus nw is greater than n. N is strictly greater than half. Of course, you could have picked read quorum other ways, but we will assume that the write quorum is always bigger than the read quorum. Okay? So I'll show you some examples. Okay? But let's just understand how the protocol will work. First, you are going to pick this read and write quorum, and then when you want to make a write, you're simply going to contact any arbitrary NW servers out of n. Okay? Pick that chosen at random, and you are going to perform the writes on those machines. Okay? When you want to perform a read, you are going to pick NR servers at random from n, and you are going to do a read on the data item, and then you are going to check, did they all return the same result? Maybe you are reading a file, you compare the file, did they all return the same file? If there is any mismatch, you have to repeat because your read failed. Okay? But if all of them match, okay, if all NR servers return a result that match, then you are guaranteed that that is the most recent write. You can never get a read quorum where the machines agree and you're getting an old result. That's going to be guaranteed by the protocol, and we'll see why. Is that clear what I said? Okay, so here are some examples that help us understand this, right? So 12 machines, okay, A through L. Okay, 3 different examples of choosing read and write quorum. Okay. In the first example, we picked the write quorum to be 10. That means that any time a client wants to make a write, it has to pick any 10 out of those 12 servers. Doesn't matter which 10. 10 servers at random. Perform the writes on those servers, and the servers have to say the write was successful. There's no other communication. You just send the write to 10 servers. 10 servers reply saying write is done, client is done with the write. Okay. Is that clear what I said? Okay. Read quorum is 3. That means that a client can pick any 3 servers out of this 12 at random. Okay. And if those 3 servers, and say you read a file, and if those files match, you're guaranteed that that's the most recent, right? If the files don't match, you repeat. You pick another 3 servers at random. You do this until you find 3 servers that say, yes, this is the file, they all agree. Okay? And you're guaranteed now that you will get the most recent. Right? Okay? So let's take this example and try to understand why is it that the read quorum can never give you bad results. Okay? So here is an example. So let's say the write quorum is C, the dotted circle there, C, D, E, F, G, H, I, J, K, L. Okay? So you left out A and B from the write, you picked all the other 10 servers, and you perform a write. Okay? Now another client comes in, it wants to read the file. It has to pick 3 servers. Okay? It picks A, B, and C. Okay? So now you get 3 files, one from A, one from B, and one from C. And it's clear that A and B have not seen the write based on what we just showed you, because the most recent write went from C through L, right? So these 3 servers are not going to agree because C has seen the write. Okay? Its version of the file will be different from A and B. Is that clear? Right? Because the write went from C through L, so you pick 3 servers and you pick A, B, C. A and B will have an old version, C will have the new version. So this write will actually not succeed because the 3 servers will not agree. Okay? So you repeat. Okay? And if you now pick 3 servers that are a subset of the write quorum, okay, then you will succeed by definition, because all 3 servers will return the same version of the file. They all saw the most recent write. But so long as you keep picking one that's outside that quorum, you will keep failing. So you keep retrying until you pick those 3 servers that agree, and then you're guaranteed you got the most recent. Okay? So what this is telling you is that the protocol is designed in a way where if you hit a server that did not see the most recent update, by definition, it is guaranteed to disagree, because you picked the read quorum such that you will never actually pick 3 servers that did not find a write, because this is why NR plus NW has to be greater than N. Okay? And you will see that in another example where what happens if you actually don't choose it that way. Is this clear? Any questions on this? Yes, question. Yes, question is what happens if there's another write? Okay? Good question. So maybe you have another write coming in, and now you pick A through J, and you leave out K and L. Okay? So now the file gets updated. There's a new version of the file. A through J have seen it. K and L have the older version. Okay? Now another read comes in. You have to pick 3 servers that agree. If you pick J, K, L, they will not agree because K and L did not see that write, but J did see it. But if you picked A, B, C, like in this example, they'll automatically agree because that write did hit A, B, and C. Right? Yeah. The question is, it's missing one of the older writes. Is that okay? So that depends on how the write is being performed. So if the write is the entire file is being replaced every time, then it's okay. Right? If you're saying I'm going to append a character to the file, okay, and A and B didn't see the previous write and now you appended another character, that's not right. So the writes actually have to be performed in a way where the entire data item is always updated. So if these are, let's say, integers that you're updating in a database, of course it's fine, right? Because you didn't see the previous update, but now you updated a record, it's okay. But if you're actually doing reads and writes to a file, then the write has to actually replace the entire file with the new file. you can't just modify parts of the file. So long as you do that, it will be fine. There was a question somewhere here. Yes.
Why can't they just take ABC and pick the latest time?
Okay, question is why cannot we use a timestamp to do this? That's your question, right? Okay, so you could use timestamps to figure out C as a newer version than A and B, but now that has introduced an additional criteria saying the machines have to be synchronized and the timestamps have to be accurate, right? So if they, and we have the same problem, clock synchronization is never fully accurate. Like say NTP has 50 milliseconds error, right? So if there are two writes within 50 milliseconds and A, B sees some one of them and C sees the other one, you cannot actually tell which is the most recent. Right? So you can use clock synchronization here, but you will always have the problem of what we had said, clock synchronization is never absolute. There's always an error, and two events that are within the error tolerance, you can't say which is the newer version.
That particular entry has in your sites. How do we make sure whatever three values we're picking?
Yeah. So question is, if you don't have timestamps, what are we actually doing? So you can add version numbers to files. Version numbers are simple integers. Every time you update the file, you increment the version number and you write it. That's one example. So that you can get away. That's like logical clocks, right? You have an integer. Version numbers are the same as a Lamport clock at some level. So you could do other things to make sure that you have the most recent write figured out without comparing timestamps. Okay. Yes. Yeah, question is, can we use this approach if you're appending contents? If you're simply doing append and append only writes the new part to the file, this approach will not work because A and B for the previous write didn't see that write, and then maybe another write came and A and B are part of it. So you basically are now appending some content where you missed the previous append. So that will not work, right? So this will work fine for databases where you're updating records or updating integers. For files, the only way you are going to do this is each write has to replace that entire file with the new contents of the file. Then you are okay. Okay. Yes. Okay. How does the coordinator keep track of NW? There is no coordinator. This is leaderless. But the client, all the reads and writes are being done by clients. The clients are told what the choice of NW and NR is. And the rule is, when you're performing a write, you have to pick any 10 of those servers and perform the writes. When you're performing a read, you pick any 3 servers to perform the read. If they agree, you're done. If they don't agree, you repeat. Okay. Question is, are the 10 writes done synchronously? Yes, they have to be performed synchronously. You have to send that write to all of those C through L in this case, wait for the response, then the write is done. Okay? All right. Where is this protocol used? Quorum-based protocol. There we will actually look at, we haven't gotten to consensus yet, but when we start talking about things like consensus and agreement, we will see that these kinds of techniques are actually quite popular, right? So, but yeah, you can use it in any replication technique, but more to the point, these days they are used when you want to essentially get replicas to agree. You don't want a coordinator because coordinator can fail. There are all kinds of reasons. Yes, question.
Since all of these NR and NW are selected randomly, is there a performance which, because if we keep selecting the same thing, failing,
yeah,
then we have to try more.
The question is there a performance disadvantage? Unlike the leader-based protocol, there is a disadvantage, which is that reads can take multiple attempts to succeed. Okay, that's the price you pay for not having a coordinator. Right? If you had a coordinator is handling all of that for you. Here, reads will take longer, writes may not. Okay? Except we'll see a technique where reads might not take longer at all, but we'll get to that. So let's take the second example here, where we picked still 12 servers, right? So we picked the read quorum to be 7, the write quorum to be 6. Okay? So the dotted lines are the write quorum. So DHLIJK is the write, the most recent write. Okay? You pick those 6 servers, you perform the write. Now you got to perform a read. So you will pick 7 servers. Okay? And you will see the first 7 that you picked. Are they going to agree? So they will not agree because H has seen a more recent write than the other. So they will fail. Right? And you can retry, but it will still keep failing. Okay, because there's no way to pick 7 servers where they will all agree, because you will always pick one of the right quorum, and no matter how, at least one, maybe more, and you'll pick some of the other ones, and they will always disagree. Okay, so the right in this case never succeeds. So what's the problem here? Well, first problem is we picked NW to be 6, is not a strict majority. Okay, we said it has to be strict majority. Okay. Second problem is we picked the read quorum, as was pointed out, to be bigger than the write quorum. The read quorum is bigger than the write quorum. There's no way to pick servers where they all agree. Because you'll pick 6 plus at least one that will disagree by definition. Okay, which is why we need to follow these rules here. Okay, the sum has to be greater than n. NW has to be strict majority, and the read quorum has to be smaller than the write quorum. It's the only way you will succeed. Is that clear? Okay. All right. So last case is the third example. A write quorum is the entire set always. Okay. So all the writes go to all the replicas. The read quorum is 1. You never have to ask more than one server if all the servers have always seen the write. Okay. So writes here will be broadcast to all the machines. The reads are going to be local. Right? This one is called read one, write all. So you will always write all, okay, and you will only read one. So this makes it more efficient to not retry reads. But writes are expensive. They have to go to all the servers. So reads are cheap. You never actually have to check with any server because you know that every server got the write. Is that clear? Yes. Okay. Question is, what happens if NW is 11, NR is equal to 1? Okay. And you go to the server that didn't read. Okay. That will not work. That will return bad results. Okay. And the reason it returns bad result is we did not agree with that rule. NR and plus NW has to be greater than N. If it's 11 and 1, it's actually equal. Not, that is why if you pick them incorrectly, you will get bad results. But then if you're getting wrong results, you got to go and say, did I follow the rules? If you follow these rules, that should never happen by definition. Okay. But that's a good point. Any other questions? Yes. The question is, if you're doing multiple writes, is that a varying coordinator? So the way you want to think about this is the client is doing all the writes. There is no coordinator. The client knows all 12 machines. Think about, let's say you write a Python code, right? So you are doing some write to a file. Your Python library actually has to send, in this case, 10 writes to 10 different servers. Okay? It can pick those 10 servers any way it wants. So it is going to send those 10 writes. It's going to wait for the response. When all the 10 writes return, it will tell the client the write is done. Okay? The read is the same way. You will try to read that file. Okay? You will go and pick 3 servers at random, read the file. You will compare either the version number or the contents. If they match, the library will say, here is the write. Okay? If it doesn't match, then it will retry. Okay? So there is no server that's acting as the coordinator. The client through a library is doing all of this. Right? Okay? From a user's perspective, you're still doing reads and writes. Internally, it might translate to multiple reads and writes, but that's not an issue. From a developer is not writing 10 writes in the code. Right? You only write once, and then the library is going to do this for you. Is this clear? Okay. Yes. You're saying if the writes are concurrent, should you write to all the servers? Is that your question? Yeah. So question is, if the writes are concurrent, should we write to all the servers, some subset of it? When there are concurrent writes, you still need a way to order the writes, okay? And make sure that writes at least get increasing and unique sequence numbers. So let's say current version of the file is 10. Okay? If two clients read this file and says version 10, and each of them says, now I'm going to write a new version called version 11, and then you are overwriting each other. So that's bad, clearly. You don't want that to happen. So long as you have a way to deal with this, right, maybe through locks or other higher level mechanism, you can have concurrent writes, but you need to make sure internally in the system they're ordered in some way. You don't want two writes to overwrite contents, like the example I just gave. Okay, yes. If the client, from a client's perspective, the writes are concurrent, right? So the client picked 10 servers in the write quorum, and it's written, so the library is sent 10 writes in concurrently and is waiting for the response. Same as what happened in the replicator. Yes, those will be, you're not sequentially writing to C and then D and all that will just take a very long time. You just send 10 of these requests in parallel to 10 machines. Okay, question is, in that case, is write all expensive? That depends on what cost you want to pay, because you will have more writes going out, but the reads are simplified, right? So this goes back to, you have to look at your workload. If the workload is read intensive, writes are infrequent, then it's better to actually go with that approach, because you will write to all 12 servers, but your reads are very cheap. You only read from one server. Okay? But then if the opposite were true, if it was very read intensive, very write intensive, then you may not want to pay that price. You might want to pick smaller write quorums, so you have cheaper writes, but then reads might have to retry, but they're not that frequent, so you can pay that price. So that's going to depend. So how you choose NR and NW is left to the application developer, right? So long as you follow that rules, there are many ways for this 12 to have picked. So you could have picked NW is 8, NR could be 4. There could be many ways you pick this, right? So how you pick it is based on what you expect your read and write frequency to be. Is that clear? Okay. All right. So that's Gifford's quorum-based protocol. The first time we actually came to a protocol that involved voting and agreement, right? So we are actually voting on A, B, C. In this case, in that first example, are voting on, is the read going to succeed? Are these the same file version numbers and things like that? We are going to come back to this, okay, when we talk about failure recovery and consensus and things of that sort. So there's a lot of this kind of voting based techniques that we are going to see. This was the first time we encountered it, okay, but we will see it many more times. Okay, so I'm going to skip this because we already saw what happens, but just to be clear, in this case, if you're doing the read has gone to maybe some, not all the machines are shown here, of course, only 3 are shown. That was a read quorum. You will ask them, they will all return the version numbers, and you'll see if the version number doesn't match, which was the first example I showed you, then you are going to essentially not look at it, right? So, and then you are going to try to figure out what you want and so on. Yes. Yes, in this case, you're right, it's not coordinator. So this is really the library of the client. It's not really a coordinator, but the client library is dealing with, right? But that's a good point. All right, so I'll skip this, but we'll talk about replica management and then talk about failure recovery and other techniques. So we looked at remote write protocols, we looked at local write protocols, we looked at leaderless write protocols, which are quorum based. Okay, so all of these try to figure out how do you perform reads and writes. But replication involves many other things that you got to worry about, not just consistency and how are you going to perform reads and writes. Are they synchronous, asynchronous, leader based, leaderless? Those are all good things to think about, but there are other things you want to figure out. How many replicas to have in the system? Okay, that example I just showed you had 12 replicas, okay, for quorum based protocol. Why 12? Right? Why should it be 5? Should it be 10? Should it be 2? Okay, so somebody has to figure out what is the right number of replicas to have for any application. Okay, just as when you had thread pools, you decided how many threads to have. Right? Threads gave you some notion of concurrency. In replication, you have to also figure out how much replicas to have, because they are going to give us other techniques like scaling up or the ability to do failure recovery and so on. Okay, that's one thing. Okay, the number of replicas. The second is, should all the replicas be at the same location, or should they be distributed? Right? That also has some implications on what the cost of reads and writes could be, right? You could put all the replicas as machines in the same data center, the same cloud or same location, right? In this case, communication between replicas is fairly cheap because they are actually in the same location, okay? But if that entire data center goes down, okay, you can't actually do anything because you put the replicas, right? So but they are at the same location, so you can deal with server failures when you have replicas at the same location, but you cannot deal with data center failure. Maybe the power went out, okay? The entire data center, all the machines are down. So the fact that your replication didn't really help you in this case, right? But if you put the replicas in different locations, right? So now if one data center goes down, some other replicas are still up, right? So you can still go and get your data, right? But consistency becomes harder. So this goes back to, if you're doing synchronous writes, your writes are now going to all kinds of locations, right? But that is actually going to increase latency for writes and so on, right? And if you're doing quorum-based reads, your reads are also going to all kinds of locations. You're actually getting the results, voting, and so on. So you can do geographic replication, okay, where you put the replicas in different places, but that will actually come at a cost of consistency maintenance and reads and writes and so on. Okay? When we talk about the web, we will actually look at this problem. We will see how do you put these replicas in different locations. What happens if you put them in the same location? How many replicas to put? Okay? Should the number of replicas be varied dynamically? Right? Just as in your thread pool, okay, dynamic thread pools, the number of threads is changing based on load. Okay? You can do the same thing for replication. Okay? When the load is high, you can create more replicas so that the load gets spread across all the replicas. Each replica is handling a fraction of the load. Okay? And when the load goes down, you can reduce the number of replicas. So the size of the replica pool can also vary based on how much demand you're seeing. So you can do on-demand replication and so on. So there are all kinds of other techniques that we got to worry about in addition to consistency and reading and writing in a consistent manner, which we have looked at. Okay? But these things we are going to differ. We are not going to talk about it necessarily now. A lot of this we will come back to and look at it from the context of the web or the cloud. Okay? So that's where I think it's better to see the techniques in the context of a specific application rather than thinking about it more generally, right? But as far as replication is concerned, that's all we are going to talk about now, but we'll revisit this when we talk about the web. Okay? Instead, what I'll do for the rest of the class is to talk about another facet of replication, which is fault tolerance. What do you do when some of the machines go down? How are we going to deal with this in our distributed system? And we have replicas, so we know some of the machines stay up, so you can deal with that. But first, I think what you should realize is if you're single machine systems, no fault tolerance, no ability to deal with fault. Machine goes down, application is down. Okay? That we talked about in our very first class. But now you have a distributed system, multiple nodes in the system. Okay? So partial failures are possible where some subset of the nodes go down. Can the system continue to run? Right? We just talked about the quorum-based protocol. We had 12 machines. What if 2 failed? Okay? Can the system continue to run? Perhaps. Right? If you pick the read and write quorum the proper way, it should continue to run without any problem. Okay? So there are many other techniques that we can think about, locking or all these other things we talked about, where we need to see how to handle these failures. Okay? What do we do? Right? How do we automatically recover from them? Now, the reason this is important is that when you have larger distributed systems, the probability of a failure keeps going up. Okay? And this is a simple equation, but it's something you have to keep in mind, which is if you have n components in your system, n machines in the system, the probability of a failure is the probability that any one machine fails. Okay? That's what a probability of failure means. One or more machines fail is a probability of a failure. Okay? And that's basically 1 minus probability of no failure. Okay? And you will see that as n goes up, that number is actually going to trend to 1. Okay? And the reason is, let's say P is the probability of a machine staying up. Okay? So Probability of a failure is 1 minus p to the power n. So this is 1 minus p to the power n. So p means no failure. So the p to the power n is none of the machines have failed. 1 minus p to the power n is some machine has failed. Okay. Now as n goes to infinity, which means that the system size is becoming larger and larger, what does this term become? Okay, it's going to trend to 1 because p to the power n, p is strictly less than 1, right? There's some probability that it'll stay up. It's not 1. There's always a chance of failure. So this is a number small as a fraction, right? Fraction to the power n, as n grows, that term will always go to 0. Okay, so this term is going to go to 1. What does this tell you? In any large scale system, okay, failure is actually a common case, not an uncommon case. If you have one machine, right, you don't expect your laptop to be a failed as the common case. The common case is that you will essentially expect your machine to work, and maybe something goes wrong once in a while, it might fail. Okay? But you may have a system with 100 machines. Chances of one machine failing is now actually not insignificant. Your 10,000 machines, the probability that some machines have failed is almost guaranteed. At any time, some fraction of the machine would have failed for any arbitrary reason, even independent, just because of that term. Even if those are independent failure, okay, as n grows to a large number, that will trend to 1. Okay? So what does this tell you? For any large scale distributed system, if you don't build failure recovery as part of your application will fundamentally not work, because shouldn't say half, but some fraction of the machines would have gone down by definition. And then if you haven't dealt with that by designing these into your system, then your application will not work. So the larger the system, okay, more common will be the case, a scenario where some machines are down for any reason. Disk failed, maybe the machine overheated and died, or maybe the OS crashed. Anything could, software problem, hardware problem, anything can happen, and so the probability that something will go wrong just keeps going. Okay? So fault tolerance for large system actually has to be built in. It's not an option where you say, let's assume that's a rare case and we don't worry about it. Okay? So you have to actually think about this more carefully. Okay? Now, think about, with that, what I just said, think about how we are actually used to operating machines and systems. Right? So almost every OS, okay, when it comes out, it has bugs in it. Okay? Software is never bug free, especially large software. There's always bugs. This is how software design works. Okay? And there's some assumption that we always make that every once in a while that some bug might get triggered and the software might hang or something like that. And if you are tech savvy person, you say, okay, I'll just reboot this machine or something like that, and maybe things will come back to normal and you just move on. Okay? But that's not how people actually are used to dealing with any system they work with. So let's now assume that distributed systems have become pervasive. So almost anything you buy actually has a piece of software in it and a computing device built in. So let's say TVs are now smart TVs, right? So it is basically a computing device. Okay? So if you tell somebody saying every 3 days your TV will hang, you got to restart it, they are not going to be happy. Okay? Let's now take an even more extreme case. Let's say all cars are also computing devices because they all have sensors in them. They all do compute. They can figure out all kinds of things like crash detection and do automatic braking, etc. So they run a lot of software. Okay? If you tell somebody saying every 4 days you got to reboot your car, that's not a thing that they understand what that even means or why you got to do that, right? So what we are used to in terms of laptops and PCs don't translate to the real world, because that's not how people deal with devices that are actually inherently unreliable because they're buggy, right? So you don't want to build your systems in a way that requires the users to take these types of action. You want higher levels of reliability in your system. Okay? So we are not going to worry about how are you going to make your car or TV better, but we will think about how are you going to make your distributed system better, because that can be worse. If your bank goes down, you are not happy because you can't access your money, right? If you go to the ATM and it says, okay, machine is rebooting, come back after 1 hour, that's not a thing that you really want to hear. So you want your systems that we build to be very reliable. Okay? So that's really the reason we want to think about fault tolerance for a distributed system. Is that clear? Okay. All right. So I'll explain some more concepts, and then we'll talk about some very simple techniques today. We'll come back next time and talk about more sophisticated fault tolerance techniques. Okay, so, but first thing is some terms that you need to understand. And we'll talk about availability, reliability, and safety, and we'll also talk about maintainability, all of which seem like good things to have, because maybe I haven't defined them, but they all look like good properties. So let's see what they mean. Okay? Availability means that the system should be available for use at any given time. Okay? So it just, if I go to a system, is it up or down? What's the percentage or probability that it's up at any given time when I try to access the system? Is always expressed as a percentage, right? So typically, you want the system to have high availability. It's never going to be 100% because there's always some chance the system will fail. Okay? But the closer the availability is to 100%, the more available your system is, because the chances it are down are much smaller. Okay? So usually, distributed systems that have high degree of fault tolerance built in, okay, will have high availability, and this is usually expressed in what is called some number of nines of reliability. So here is a number which says 99.999% reliable. That is called 5 nines of availability. Okay? That if a system gives you that guarantee, that means that the maximum downtime it can have is 6 minutes per year. 6 minutes per year translates to 99.999% of the time in that year that it's up. Okay? That's a very high number to shoot for. That's basically some of the most reliable systems give you 5 nines of availability. So you could say, I want less, so you'll have 4 nines of availability. 99.99 will actually buy you more than 6 minutes. You can be down few hours of the year. Okay? Still pretty reliable. Okay? Think about, like, you can only be down few hours every year. A system has to run even if some components fail and so on. So you could do 3 nines of reliability. That's 99.9. Okay? That means that you can have some days where you can be down. Okay? Still pretty reliable. Even 3 nines of reliability is actually pretty high to achieve. Many systems don't even get to the 99%. They'll be even less than that. But the most reliable systems you build, you provide guarantees in terms of how reliable it is, and usually you think about some number of nines of reliability. So this is what availability means. Okay? Reliability here basically is a related term to availability. It simply says the system should run continuously without failure. Okay? Now, as I said, you can have a distributed system. Not every component is going to be 100% reliable, because components will fail. I just showed you, even if there are independent failures, if n is large, there will be some independent component failure. The system as a whole should continue to run. That's what reliability means. Okay? If you have a reliable system, it will automatically give you higher availability, because even if some components fail, it's continuing to run. Okay? And as a result, users can access it and do their work. Okay? Safety essentially is a related term. It says temporary failure should not cause catastrophic failures. Okay? This means that there should be no single point of failure in the system, which means if that machine goes down, the entire system is down. Right? So that's not something you want in your system. You want every component to be replicated, so that any component that's not replicated in a large system is a single point of failure, because if that machine goes down, that's the only component in the entire system that deals with that task. The system as a whole can actually fail. Okay? But if you want to have safety properties, that should not happen. Some small number of components failing should not bring down the entire system. Okay? That's called a safety property. And you need the safety properties when you have mission critical system like an airplane. Right? And airplanes are built with very high levels of redundancy. Even if an engine goes down, the plane can fly. Okay? Or if some component and the engine fails, sometimes there are 3 other components that can take over. Right? There are 4 degrees of replication, and so they have high degrees of replication to ensure high amount of safety. Same with the nuclear reactor. You don't want some computing software to fail and the nuclear reactor to have problems. Right? So when you build these kinds of systems, you really pay attention to how do you build very reliable, safe, and available systems. But when you build software systems for other things, that's not the case. right? You basically ship systems with lots of bugs in it and let the user deal with it, which is not how it should be. Okay? But so you want to make sure that you want your system to actually be fault tolerant and have all of these properties. This question. Yes. Right. The question is, how is the availability guaranteed? Is it statistics or is it based on some analysis? So technically, it's a combination of the two. If you actually build some degree of replication in your system, you assign some probabilities of failure to the system, then you can actually do the math and say this is what actually can be guaranteed. The problem with that analysis is that there should not be correlated failure, right? So what I showed here assumes these are independent failures, right? Correlated failures means if I have 100 replicas, they are all one location, the power goes out, the entire system is down, right? So, but so you want to make sure that when you do this analysis, that these are all independent failures. So if you don't catch correlated failure, that can cause cascading failures, which means one component fails, it basically causes other components to fail, system goes down. But if you do the analysis right, you can come up with an availability guarantee. But then that availability guarantee is also measured, because you built a system and you told your customer, I'm giving you 5 nines of availability. At the end of the year, they may show me that you actually gave me that, and then you have to measure it and say, look, you had 3 minutes of downtime, so I am actually under the 5 nines of reliability. So it's both ways, but yes, it can't just be measured. Then you don't know what you build the system for. Yes. Can availability be 100%? Typically not, because you cannot assume a component will never fail. That any hardware or software is prone to failure. That machine might die for any arbitrary reason. So you cannot guarantee 100% always. Okay, you'll always have some small failure probability built in. Yes. Okay, question is higher availability is higher reliability or other way around? So you start with reliability. The more reliable your system is, which means it runs continuously without failure, even if some components fail, you get higher availability, right? Or to put another way, if you want higher availability, you want to ensure that your system has higher reliability. That's the way you're going to get availability. Okay, and reliability is going to be through replication and fair fault recovery and all of that. We'll look at that. Okay. Maintainability is the last term there. That just means that if there's a failure, you should be able to recover from it. Okay, so and fix the problem. All right. So with that, we'll talk about some more terms, and then I'll show you some very simple techniques to do some fault tolerance. Okay, the 3 terms we'll talk about are transient faults, intermittent faults, and permanent faults. Okay, so the transient fault essentially means this failure, as the name suggests, is transient. Okay, the failure just comes and goes. Okay, so this could be like a bit flip in memory, right? If you have RAM, you will know that there are some arbitrary fault where one bit just flips automatically, goes from 0 to 1, so that whatever is stored, word or integer is stored in that location, memory has changed, okay, because the bit just flipped. That's an error that can occur in RAM. So but that's not a permanent fault, that just happened once in a while. Okay, so there are many kinds of transient faults where the fault just happens one time and it's gone after that. So that's called a transient fault. Intermittent fault means this fault is not permanent, but it's occurring every once in a while. Okay, so maybe it's your car, when you're turning, it squeals or something like that, right? So that's kind of, but when you're driving normally, it does not give you that problem. So these are faults that recur from time to time, but they're not there the whole time. So that's why they're called intermittent. Okay, and permanent fault means that the failure has occurred and some component has actually failed, right? So basically, in terms of time, this means that component is dead, right? Some part of the system actually failed. This means that maybe the component is failing every once in a while, it doesn't work, but then it works for some period of time. This means that the fault was one time. It just happened once and it's not happening again. Okay? So several different types of faults that we want to think about. We want to worry about all of them, okay? But permanent faults, clearly you need to really deal with. Okay? Then the other kinds of faults is what type of fault it is, not whether it's permanent or transient, but what caused it, right? So one type of fault is a crash failure, okay? Software crashed. That's a type of a fault. So server just stopped working. Okay? This is called a crash failure. Okay? Then there is an omission failure. Omission failure means that the server did not respond. As you sent it a request, the server is up, it doesn't crash, it did not send you a response. That's called an omission failure. Okay? Timing failure says the server is slow. You sent it a request, you would like a response within certain amount of time, let's say half a second or 100 milliseconds. The server is taking much longer to respond. It feels really slow and sluggish. Okay? It's a type of a fault, right? Because server has become very slow. Okay? Timing failure. Okay? Response failure is very similar to omission failure. It says that, but it's giving you an incorrect response. Okay? It is responding. You ask it some question, it's sending you a response, but the response is wrong. Okay? Maybe you send it an RPC request, it gave you an incorrect response. Okay? An arbitrary failure, which is the worst type that we will deal with, also called Byzantine failures, is saying that the server may produce arbitrary responses at arbitrary times. Okay? Sometimes the server looks like it's working well, giving you correct response. Other times it's sending you garbage. Okay? And you can't tell when it will do the right thing and when it will do the wrong thing. It could be because there's a bug. It could be because somebody has actually hacked into the system and they are doing malicious things. There could be any number of reasons why this type of failures occur. Okay? These are the hardest ones to see that we'll have to deal with. Crash failures, as we'll see, okay, although it sounds like something bad has happened, from a failure recovery perspective is the easiest one to deal with. Okay? So various kinds of failures. We'll come back to them, okay, next time. But today I'm going to end with this slide, which just shows you how do you deal with this in hardware. Okay? And we will use the same technique when we design software. Okay? So here is a circuit. Okay? There are two figures here, one at the top and one at the bottom. The circuit essentially has three components. It's a hardware circuit. You don't need to know anything about hardware to understand this. But let's say that a circuit has three components, A, B, and C. Okay? Each input takes one bit as input and it produces one bit as output. Okay? So each of these components is performing some operation and is taking an input, is producing a one bit output. So there are three stages to this circuit. Okay? So in this case, so if the circuit is designed this way, if any A, B, and C fail, the circuit stops operating. Okay? Because there is no redundancy here. Let's say B just stops working, permanent failure. Circuit doesn't work anymore. You provide it an input, there's going to be no output. Okay? Or there is an intermittent fault where, let's say, B is randomly producing bad results every once in a while. Okay? Circuit will still sometimes seem to work, sometimes not work. Okay? Again, you have a problem. Okay? So this clearly has no fault tolerance built in at all. Okay? So now we have a different version of this circuit, okay, where we have replicated each of those components. We have three replicas of A, A1, A2, A3. We have three replicas of B, three replicas of C. Okay? So we'll take each input, we'll feed it to all three copies of A, B, and C. Each of them will produce an output. Okay? We will take a vote and we'll take a majority vote. Okay? Even if one fails, the other two will agree. Right? Because if one of them fails, the other two. So if you just take a majority vote, so long as two of the three are agreeing, we'll say that's the output of that stage and we'll feed it to the next stage. Okay? So we'll put a voter in the middle of each of these. So you replicate A, B, and C three times. Okay? Every input is fed through all the replicas. You take the output and then you vote, and then you feed the output of the vote, majority vote, to the next stage. Okay? So you put a voter, okay? But you can't have a single voter. Okay? You will see there are three voters here. Why can't you have a single voter? Yes, the voter can fail. Why would we assume that the voter, that's a single point of failure? Because all circuits, right? So anything can go wrong. So you could have, in theory, just have one voter, and you will see that A1, A2, A3 will go to V1, and you could have taken that output and fed it out. But if the voter fails, you have the same problem. Okay? By replicating A, B, and C and having a single voter, you have not solved the problem, which is why you have three of these as well. Okay? So you will take the output of all three, you will feed it to each of the voter. Each of them will take a majority vote, it will feed it to the next stage and so on. Okay? Now in this, so you will see that's happened at each of the stage. So in this circuit, this is called triple modular redundancy, which means that there is it's called TMR. So there is three copies of everything. Okay? So instead of one copy, you have 3 copies of everything. Each stage you will produce an output, you will vote, you will feed that to the next stage, and so on. Okay. So now any component can fail in the system will continue to run and operate without any problem, because if A2 fails, A1 and A3 will agree. Some voter that is not taking A2, or even if it takes A2, the voters will take the majority vote, they'll feed it to the next stage, everything runs as is, no problem. Okay. In some cases, multiple stages can also have single failures and it will work. Not always, but at least it guarantees one component failure and it's still fine. Okay. Is that clear, what I just said? So this is a way you can design a hardware circuit and actually handles hardware failures. But what you will see is the cost has actually gone up by factor of 3. In fact, more than the factor of 3, because there's voters as well in this, right? So we got our failure recovery at a high cost. We tripled the cost of the system in this case. Okay. Yes, your question. Can the system be called 100% reliable? So if this system can handle single failure. Okay. So what that means is, so long as no more than one component fails, the system will continue to run. Right. So that's what you can actually call it. So yes. But if you have more than one failure, you cannot actually guarantee. If A1 and A2 fail at the same time, then the system will stop working, because they might both produce the wrong result and the voter will think that's the right result and feed it. Right? So you will always design the system to tolerate some types of failure. The failure is actually not aligned with what you designed for, then all bets are off. So long as you have one failure, yes, it will work fine. Is that clear? Any other question? Yes. Why do we choose 3 copies? Okay. The question is, why do we need 3 copies? So if you want to tolerate a single failure, okay, and this is, if it's a crash failure, then you only need 2 copies, because one of them just stops responding, the other one still produces the right result. But if it's producing arbitrary result, okay, this state, let's say A1, no matter what you feed it, always outputs 0. Okay, because that's what the circuit got stuck and it's just producing 0 no matter what. Then you need the other 2 to outvote it, because you don't know what if you had only 2 copies, okay, one produce 0 and one produce 1, you don't know what's the right result, right? So you want the other 2 to outvote, so you need 3, right? So that one failure means the other 2 are working, they will actually outvote the failed one and produce the right. This is only required if you have arbitrary failures. If you have a crash failure where the circuit, that part of the circuit just dies, doesn't even produce an output, then you only need 2 copies. Okay? Because one of them has crashed, the other one is functioning, it will produce the right result. Okay? But if the arbitrary result, you need 3 copies in this case, plus a voter. In fact, more than one voter. Is that clear? Okay. So this is a very simple example to show you how we are going to build our distributed system. Okay, as you can imagine, if that was a 3-tier application, you would have to do something like this to actually produce a system that can deal with a single failure, deal with arbitrary things happening at each machine, and so on and so forth. So I'm giving you this hardware example to tell you how we are going to build our software system. There will be a high degree of replication involved to deal with different kinds of failures, and we will use voting to understand what to do at each level. Right? So this is basically going to be a simple example of how we will design our distributed system, which we'll talk about next time. Okay. All right. So let's stop here.